So we have come across two formulas now for arithmetic mean, and I'm shown a problem on each. So if you have been given with just the values of x, no frequencies, you call it as raw data. And usually in the examination, we try to give less than 10 or 15 observations so that you need not worry about constructing a frequency distribution and compute the mean. We insist you in doing the calculation by using the formula x bar is equal to total of x divided by n. On the other hand, if we have already presented you a discrete frequency distribution, then the steps of computation of mean is very much simple. Obtain the total of f, multiply f and x, and obtain the total of fx, and apply the formula that x bar is equal to the ratio of total of fx to total of f. So these are the two forms, and there will be one or two problems on the computation of mean in the examination. Now you have various problems, given in that book, and various techniques exist computation of mean, and the methods what I am suggesting you or giving you is called as mean by direct method, where I'm using the values of x only. So if I'm just using the values of x, it is called as direct method. Sometimes you can use assume mean method, shortcut methods, and various such indirect methods are there. Those methods were derived just to avoid the calculations in the earlier days where the availability of calculators or computers were not that handy. So people developed certain methods so that even for the values of x which are 4-digit or 8-digit or 3-digit number, the calculations of mean becomes very much easier without the calculators. So those are called as indirect methods. So you need not worry about that. So even if you come across any method like step deviation method, shortcut method in the particular book what you have downloaded, you need not worry. So just look into the formulas of x bar is equal to sigma x by n, and x bar is equal to sigma fx by sigma f. Now, the third type of distribution is discontinuous frequency distribution. So, if we have a continuous variable and the number of observations are very large, we try to represent the data in terms of class interval data, which is called as continuous frequency distribution, also called as grouped frequency distribution. Now, if you have grouped frequency distribution, we assume this value of x to be the midpoint. So you have been given with class interval and frequency. Now, as far as possible, we try to give you the exclusive class intervals only. By chance, if you have an inclusive class interval, convert that into exclusive class interval and obtain the values of x. And here we assume the values of x to be the midpoints of the class interval. And this midpoint is the middlemost point of the class interval, and that is obtained by the formula or the average of upper and lower limit, which is sum of upper and lower limit divided by 2. So for example, if you have a frequency distribution like 0 to 5, 5 to 10, 10 to 15, maybe 15 to 20, 20 to 25, with some frequencies, say 1, 3, 4, 2, 1, then the computation of mean is solely based on the midpoint x. Now, the number which is exactly in between 0 and 5 is 2.5, and if you want to obtain it mathematically, you add those two values divided by 2. Next, you'll have 5 plus 10 divided by 2. 5 plus 10 is 15. 15 divided by 2 is 7.5. Now, the middle number in case of the next interval is 12.5, 17.5, 22.5. So these are the values of x. Now, the reason why you consider these points for the computation of your mean, why not any other value from the confidence interval? Again, it is because of the property of central tendency. What is central tendency? If you observe a data in a group, you will observe that there is a central value towards which all other numbers are concentrated, and that's why we assume that all the numbers or whatever you are observing the count, they are very much close to the middle value. So here I'm assuming all the three values which are in between 5 and 10 are closer to 7.5. So only with that assumption I could compute the mean. Once you compute the midpoints for this class thinkable data, then you proceed as usual. So compute the total frequency. You will multiply f with the respective value of x, obtain the total of fx, and use the same formula. X bar is equal to sigma fx divided by sigma f to calculate the value of mean. So this is how we compute the arithmetic mean. And as said, these methods, these are evaluated or they have evolved uh, in the days where the calculations of mean was very much difficult and much of the manual works has to be done. Therefore, these certain assumptions are made. But when you look into the much of the practical situations, I could have my original data from where this distribution is obtained. So instead of say the number in between 0 to 5, maybe 1.5. The values which are in between 5 and 10 are 5.1, 9.1, and 9.6. The number in between 10 and 15 are maybe 12, 13, 11, and 11.5. So this could be my data. So if you look into this now, the assumption whatever you are making that the values are very much closer to that is failing. But if you look into the total now, say 3 into 7.5 or the total 4 into 12.5, that will be very much closer to the sum of these values, and hence we say it works in a large run. So if you have really large set of data, whatever the mean you compute, either by considering the original data or by considering the formula sigma fx by sigma f, the mean comes to be almost closer. This is about arithmetic mean. And coming to the properties of arithmetic mean, the only measure x bar is such that if you divide, if you subtract this x bar from every value of x, the total always comes to 0. And this difference is called as deviation.
ಸರ್ ಸೌಂಡ್ ಕೇಳ್ತಾ ಇಲ್ಲ ಸರ್. ಹಲೋ.
Are you able to hear now?
ಎಸ್ ಸರ್.
Yes.
Okay. There was some problem with this microphone. No. So these are the two important immediate properties what you could observe only in case of arithmetic mean. So after computing the mean, you subtract the value of mean from every value of x and take the total. That total will be always equal to 0. And if you are working out this for a frequency distribution, in that case f into x minus x bar, that total will be equal to 0. Now before taking the total, you square those deviations and then take the sum. That will be minimum compared to any other square deviation. So we'll just understand what it means here. So I'll take some data and show you how it works. You have x values, say 10, 12, 14, 15, and maybe 16. equal to 5. So that divided by 5 gives you x bar as 13.4. Now from every value of x, subtract this x bar, write that number and obtain the total. Now first value of x is 10. 10 minus 13.4 is minus 3.4. And then you have 12 minus 13.4 minus 1.4, 14 minus 13.4, 0.6, 15 minus 13.4, and 16 minus 13.4. If you add them, so you have minus 3.4 minus 1.4, so that gets subtracted to minus 4.8 plus 0.6 plus 1.6 plus 2.6 produces 0. So this happens only if you take the deviations from x bar. On the other hand, if you take the deviations from any other measure like geometric mean or harmonic mean, or for the sake, let me take say median here. Here median, the middlemost value when the data is arranged in increasing order is 14. So if you subtract every value from 14, you will observe that the total is not equal to 0. It's coming to be minus 1. So this sigma of x minus, if you are telling that you have subtracted the values of x from a point called as A and you are observing the total as 0, then naturally or necessarily this A will be equal to your x bar. That is the other way to interpret this result. Now, instead of taking the sum directly, if you square it and then take the sum, we are doing the squared deviation. So subtract the value of x from x bar, you will square it up. Now, whenever you square, the negative value becomes positive. It is minus 3.4 whole square, which comes to 11.56. Then 1.4 square, 1.4 square, and 1.4 into 1.4. Then 0.6 square, 1.6 square, and 2.6 square. And now if you look into the sum, that will be sigma x minus x bar whole square. And if you look into the total, it is 23.2. On the other hand, you can compare this. I said this will be minimum. Minimum in the sense, if you are comparing the same number with the same case of square deviation, instead of any other number other than x bar, that will be minimum. And I readily have the values of x minus m here. So I'll see what happens to x minus m whole square. So I have minus 4 whole square, which is 16, 2 square, which is 4, 1 square, which is 1, and 4. So if you look into the total is coming to 25. So if we just compare the values now, minimum number is 23.2 of these two. Now for that matter, instead of median, you take any other number. So instead of median, if I say I'll subtract these values by an assumed number, which we call as assumed mean, say 15, or any other number which is not at all x, like say 5 or 100, you will see various values, but the total will be never equal to 0. And if you square those deviations and obtain the total, that will be always more than this. And hence, we use this measure, which is sigma x minus x bar, in obtaining the measures of deviation. And the most commonly used measure of such deviation is average deviation. So we call average deviation. The concept of average is again simple. So we said I'm averaging the variable x. So when I say I'm averaging the value variable x, I mean I'm taking the total of x and I'm dividing it by n. I'm dividing it by n. So that is called as arithmetic mean. Now you can average any such property. So if I have any other, say, variable, which is say x minus x bar whole square, which is called as the squared deviation of observation from mean. Squared deviation of observation from mean. You can obtain the average of that also. So average of any variable will be sum of that variable divided by n. Similarly, if you have another variable, say z minus a, you can compute the average of that z minus a. That will be equal to sigma z minus a divided by n. Now, since this sum of square deviation is minimum, we could compute the average of that, and we call that as a measure of spread or deviation, and we call it as variance. So that's why we need x minus x bar whole square. So we'll discuss this x minus x bar whole square in detail, even for the frequency case, when we look into the measure of dispersion. Now the next measure is geometric mean, simply indicated by GM. I'll just look into the case of raw data, and I'll just give you the definition and few simple examples. So if you have recorded the values of x1, x2, xn, then you can define the geometric mean of that set as nth root of the product of the variables. So I have to multiply all the values and take the nth root. Say for example, if you have two values, say x is equal to 4 and say 8, then geometric mean of these two is defined as square root of 4 into 8. Now 8 into 4 is 32, and square root of 32 produces 5.65. So if you look into the value of AM for those two variables, it will be the sum divided by number of observation, which produces 6. So always you can observe that geometric mean is a numerical value which is always less than or equal to the arithmetic mean. On the other hand, if you have say 3 observations, I have 2, 5 and 6. In that case, geometric mean is defined as cube root of ಎಷ್ಟು values ಇರುತ್ತೆ ಅಷ್ಟು root ತಗೋಬೇಕು, ಅಷ್ಟು numbers ನ multiply ಮಾಡಬೇಕು. Now when I obtain the product, 2 into 5 is 10, 10 into 6 is 60, and cube root of 60 is equal to 3.9. Now some of you might wonder how to calculate this cube root. So your calculators need not be supportive, so that's why we'll not look into the details. So it becomes easy if you're dealing with 2, 3. If you have say 10 observations, 20 observations, then you'll talk about 20th root, 30th root, and so on. So the complexity in the calculation exists. So in order to simplify that, we use the concept of logarithms to simplify the values of the, to simplify the formula of geometric mean, so that the value of geometric mean can be easily obtained. And we'll just understand the definition, and we'll see why do we need geometric mean when we already have arithmetic mean. So as said, one of the major disadvantage of this arithmetic mean is that it gets affected by the extreme value. So if we have the presence of extreme value in the data, that value gradually, takes the value of mean or attracts the value of mean towards that extreme number. Or the other way to put this extreme situation is that if at all you have set of values, say x1, x2, xn, and if you are computing the arithmetic mean, then x bar, the arithmetic mean, it treats every value equally. So that is the reason it treats that very large value, it treats that very small value, as well as the other normal values to be same. And that's the reason it gets fluctuated because of the presence of extreme observation. But when you look into the definition of geometric mean, we are multiplying them and we are taking the square root. Now when you talk about square root, cube root, nth root, the extreme observation, however small or large it is, it doesn't affect the end value of the geometric mean. Or the other way to put it that it doesn't treat every value equally. Now, whenever we have the case or a measure which doesn't treat every value equally, so if at all you are talking about the presence of extreme values in the data and you have a situation where you cannot delete or omit that extreme value from your data set, then you can go ahead and compute geometric mean for that set of observations. Now, geometric mean assigns lower values for, lower weightage for high values and higher weightage for lower values so that it somewhat balances. So what I mean is, if you have certain x values which are very small in magnitude and you have some observations and you have some values which are very large, in that case, if you calculate geometric mean, so it gives higher weightage for this, higher importance for this, lower importance for this, so that on an average, the values are getting balanced, and whatever the mean you compute as geometry mean, that will be very much closer to the normal values. So that's why we need the concept of geometric mean. And also, when you look into the cases where you're talking about special variables, like say your X is the growth rates of certain bacteria or microbes in a laboratory, or you are looking into the values which are ratios or which are percentages, which are rates, in those cases, the values will be very large. So if you talk about the growth of, or the count of bacteria per every square centimeter in your experimental plot, the count could be in terms of lakhs. So you could have certain cases where the count is in hundreds, certain plots where the count is in lakhs, and certain cases where the count is in thousand. So you have extreme values. So growth could be, if you are recording x values in such a scenario, the suitable average will be geometric mean. Now, similarly, when you talk about the ratio or the percentage increase, percentage decrease of certain stock values or the price values, in those cases, we say the suitable average again is geometric mean. Another average, and the major disadvantage of this geometric mean is that if you have negative values, you cannot compute the geometric mean. In that, it is solely based on the product of the observations. So if you have any x is equal to 0 or negative, then obtaining the nth root of 0, it becomes 0. So GM will be 0. So this is the case, only case where geometric mean cannot be computed. But in most of the cases, as I said, we'll be dealing with such data. Very rarely we observe the value 0 and negative cases. We need not worry. Now, another such average is harmonic mean. It is almost similar to the concept of arithmetic mean, but here again, to balance out the effect of the extreme values, we take the reciprocal of the value. So if I have the variable x, we define its reciprocal as 1 by x, and we use this 1 by x values in obtaining the mean. And then we define harmonic mean as n divided by sigma 1 by x, and for frequency data, either group frequency or discrete frequency data, the formula to compute harmonic mean is sigma f by x. So these concepts of GM, HM are not included in your model. You could just have the knowledge and the formula is sufficient. Here we look into the cases where we are talking about average speed, average velocity, the time, distance. So if your variable are related to the vector quantities like this, in that case, we talk about the harmonic mean. So you, for the sake of examination, you have to completely go through thoroughly the concept of arithmetic mean. What is arithmetic mean? How to compute the mean for various cases, raw, discrete frequency, as well as continuous frequency, and then properties of arithmetic mean, and then the next measure, which is median. So we already observed the definition of median. It is the middlemost value. It is called as the central value also because it is also a value towards which all other values are concentrated. Therefore, we call median also as a measure of central tendency. And we looked into the calculation of median for raw data. That is, if you have x values, first you will arrange them in the increasing order. Now, once you have your x values arranged in the increasing order, you pick the middle number. So if you have odd number of observations, the middle value can be easily obtained. If you have even number of observations, obtain the average of those two middle number. That becomes the value of median. When you have a frequency distribution, then the computation slightly varies here. So I'll only talk about discrete frequency distribution. We'll not look into the calculation of median and mode for the continuous case. This is sufficient. So the F actually monitors the position also. It counts how many times a particular value is repeated, and it also gives you the position where the values are changing. And that could be monitored by obtaining the cumulative count of the frequencies. So what is this frequency distribution actually telling you is that in your observed data or collected data, you have 15 three times. Now, when I say we are computing the value of median or any other positional average or quantile, we have to arrange the values in a logical increasing order. So in the original data, I have 3 times 15, followed by 5 times 16, followed by 6 times 17, and so on. I have 3 times 19. So this is what my data is. By looking at the total, I'll have 21. So totally I have 21 values. And now if you look into the position, so from position 1 to 3, I have observation 15. Now from 4th, 5, 6, 7, 8. So 4 to 8, I have the value of x to be equal to 16. So this position is also monitored by the frequencies. So if you look into the cumulative frequency, cumulative is nothing but the sum of the frequency up to that point. So 15 is up to 3rd position, and from 4th up to 8th position, from 4 up to 8th position, which is nothing but 3 plus 8. So 16 is present up to 8th position. Now if you say 3 plus 5 plus 6, which is same as 8 plus 6, which is 14. Now in the data, from 9th position up to 14th position, I have the number 17. Then 14 plus 4, 18, 18 plus 3, 21. So the cumulative, what cumulative means? Sum. So you are adding the frequency up to that particular value of x in order to have a look into the various positions where the values of x are changing. So totally you have the observations 1 to 21. So the values are, changing with respect to these positions. So if I want to obtain the median, that will be the middlemost position. So the position for median is your n by 2. So pick your n by 2. In this case, it is 10.5th number. Now if I say 10.5th number of x, that is in between 10 and 11. Now if you look into the data, up to position 8, I have 16. From 9 up to 14. From 9 up to 14, I have the number 17. So the number which is present in 10.5th position is also 17. So this is how the median can be obtained. So simply to summarize this, if you have been given with a discrete frequency distribution, step 1, compute the value of cumulative frequency. What is cumulative frequency? You are adding the frequencies up to that particular values of x. So first value up to 15 another 3, up to 16 3 plus 5, up to 17 3 plus 5 plus 6, up to 18 3 plus 5 plus 6 plus 4, up to 19. The sum of these, they are called as cumulative frequency. Then compute the value n by 2, where n is the total frequency, and see or pick the value of this cumulative frequency, which is just greater than n by 2. After computing n by 2, pick the frequency which is just greater than n by 2 and pick the respective value of x. Attractive, yeah. There are several values of cumulative frequency which are larger than n by 2, but pick the one which is immediately greater than n by 2. So I'll show another problem. have some x values and f values, say 8, 12, 16, 20, 25, 27, with some frequency, say 8, 12, 20, 6, 3, maybe 4. So if you want to compute the value of median, for this, you will first obtain the cumulative frequency. So first value remains the same as that of frequency, 8, then 8 plus 12. So if you get confused, I'll change it to 7. X value not there. So 7, then 7 plus 12, 19. 7 plus 12 plus 20, 39. 7 plus 12 plus 20 plus 6, which comes to 45. Sum up to this 48 and then 52. So you have total frequency as 52. So next, compute your n by 2, which is 52 by 2, which comes to 26, and pick the value of LCF, which is just greater than 26, that is 39, and pick the respective value of x, that is your median. This is how we compute the values of AM as well as median for raw as well as frequency case. For the continuous case, it is just again based on certain assumption method. You have a larger formula, so I'll not talk about that in detail. So for you, how to compute the median for raw data is sufficient. ಹೆಚ್ಚಾಗಿ exam ಅಲ್ಲಿ ಕೇಳಿದ್ರೆ ಸಾಮಾನ್ಯ ನಾವು ನಿಮಗೆ ಕೇಳೋದು problems on only raw data, where we'll give you 8 or 10 or 12 values of x, and we expect you to compute the values like mean, median, mode, standard deviation, and variance. For those cases, so you just concentrate on the problem, and maybe you could have a problem on finding the mean for a distribution, frequency distribution, which is a discrete case. Next measure is mode, that is denoted by Z, and it is just simply defined as the most repeated value in the data. Now, when I say the concentration, if you are talking about a data where you are looking into the data like count data, so count data another, you are counting for certain property and you are accumulating the sum. Number of deaths, number of births, number of vehicles, number of female children per family, number of accidents, all such cases come under count data. Even for such count data, your x bar, your m, your gm, every measure is equally logically defined, and you could obtain the values, numerical values for those measures. But when you look into the count data, what we observe is there will be much of the repetitions. So when we have repetitions, we could have only a single number repeated many times. So what we tend to observe is that very rarely we observe the other cases of x, and in most of the cases we'll have this. Now coming to the number of children per family in the modern families, so often you observe the values around 1 or maybe 2, but very rarely you observe 3, 4. There are cases, I am not denying it, but much of the value appears around to be 1 and 2. So you need not worry about these cases because the ratio or the probability of happening that is very low. So you will concentrate only on this particular section. And in those cases, we talk about the average, suitable average to be mode, and we pick the Z value as the most repeated value in the data set. Now, if you talk about the case where you are looking into heights and weights of the children or certain set of persons, very hardly the data points will be repeated. So for some distributions, there could be no repeated values. So we say there is no mode for the distribution. In some cases, you could have many modes. So as said, in this case, 1 is also repeated, 2 is also repeated. If both are equally repeated for the same number of times, I could say 2 modes exist for that data. So the major demerit of this mode is that it is not properly defined. That is, there is no logical formula to compute that, but it's just by the keen observation.
And if my data is such that there are no repetitions in the data, then we say no mode exists. So this is one of the rarely used measure, but it has its own application. So rarely used arrow, it has its own application. So certain times when we talk about the ordinal data or nominal data, in such cases, the suitable measure will be median as well as mode. And mode comes into the cases when you are talking about the repeated values or certain cases where the concept of arithmetic mean or geometric mean or median cannot be easily applied and interpreted. Say for example, if you're talking about the data where you want to look into uh, the size of the shoe or the dress size owned by the people. So if you look into the average dress size or the average shoe size, you can look into the values. Say if you look into the average shoe size of the men, so you'll have the values, repeated values like 8 inch, 9 inch, 10 inch, 11 inch, and so on. So in this case, if you compute a value of X bar and say it is 9.5 inch, but no producer will be manufacturing a shoe with the size 9.5. So you can't generalize this result. So in that case, we say where is the maximum sale happening, or which particular size of shoe is sold maximum number of times. So we say that count to be the average, and we take that as the value of mode, and we say much of the shoe size what we are selling in our store is average comes out to be 9 inch or 10 inch. So this is about measures of central tendency. So I could see that many of you are requesting me to slow down, but these are very basic concepts. I have only talked about two formulas. X bar is equal to sigma x by n, and X bar is equal to sigma f x by sigma f. Now please concentrate on these values. So try to look into the problems on arithmetic mean. So in the book what you have downloaded, you can go through chapter 5, analysis of univariate data. So I have covered two concepts today, measures of position as well as measures of central tendency. And in the central tendency, I just want you to concentrate on the problems only on arithmetic mean and median. So when it comes to measures of position, please just look into the theory part. So understand what is a measure of position, what are the various methods or quantiles available, how to calculate them, and what are their applications. But no problems will be there, but you should know the logic behind the calculation. And when it comes to the measures of central tendency, you will have the theory part as well as the numerical problems. And for problems, you can concentrate on AM for raw data, discrete data, and continuous frequency data. So simply raw indicates only X, discrete frequency where you have been given with X and F, class interval data, and frequency, that is continuous data. So all the three methods are to be learned. And when it comes to median, just the first two are sufficient. When it comes to mode, the first part is sufficient. So do this homework today. And in your book, it is block 4, chapter 14, where they have talked about mean, X bar, as well as the square deviations. So I said I'll talk about the square deviations in detail. That comes under the next measure called as measure of dispersion. So we'll learn how to calculate that measure in the coming class. Okay, so I'll end the session here. So if you have any doubt, you could ask. It's less than 1 minute, so you can join back if the session ends if you have doubts, or else you need not log in again.